Okay, so today we're going to start to get into the really interesting stuff. Up until now, we've kind of looked at how buildings go together, and we've looked at the loads on the buildings. But now we're going to start seeing how those loads move through the building and how they move inside the members, or how those loads get from one spot to another, and how we can calculate what's happening through a member. To do that, though, we have to have an understanding of forces, vectors, equilibrium, and reactions. So that's today's lecture, and then we're going to build on that next week. This is where I think the really interesting concepts start to come. I know that this course, some people find it very difficult, some people find it very easy. I have to ask, there is someone in this class who keeps disliking all the videos on YouTube. Obviously, that's your prerogative. The only way I can make things better is if you reach out to me and let me know that there's something that I could do about it. If you don't like the content, well, that's prescribed by by accreditation. So the content is the content, and that's the same no matter what program you go through. If you don't like the format, that's something that I've worked hard at. YouTube seems to give the most kind of options on how to present the information to you. I'm trying to give you access to all the information I possibly can. If there's something you think that could be done better, I would definitely love to hear it. I know that there was a student town hall with the administration, and us as the professors are going to hear that feedback tomorrow. There's a meeting for us to hear that feedback. If you don't like me, that's something I can live with, and you're going to have to as well. Otherwise, I am happy to hear any ideas you have. If there's something that could be done better. If it's just that you don't like the course, I don't actually care, because the course is the course. If you think that there's something that could be done to make the course better, then that is something worth talking about and something that everyone could possibly benefit from. To the people who have liked the videos, thank you. That makes me feel good. Otherwise, other people can't see the likes and dislikes. It's just me. I can't see who does it, so you're totally anonymous. So you're not in any trouble for disliking the videos. Like I said, it's totally your prerogative. But if there's something that you think that can be done to make it better, share that and let me know. So let's go on with today's lecture. To start, we're going to talk about forces and vectors. And to really understand why we need to talk about this, we're going to talk about the entire principle of how we analyze buildings. And that principle is called statics. Or it is static. It is staying still. Not static electricity, but static in that it is staying still. The definition is the branch of mechanics that is concerned with the analysis of loads, force and torque or moment, on physical symptoms in static equilibrium. That is, in a state where the relative position of subsystems do not vary over time, or where components and structures are at a constant velocity. Basically, they stay still. We're going to build on that premise because we know there are loads acting on things, trying to move them. You know, our gravity loads are trying to push our building down into the ground. Our wind loads are trying to slide our building and tip it over. So we know something must be happening to stop that from happening. There must be something going on so that those things don't happen. So we're going to touch on that at the end of this lecture, and we're going to move on to it even more in the next lecture. But that is the basic premise, and we're going to see how we can relate that concept into a mathematical equation. And it's going to look scary when we start writing this "it stays still" equation out, because there's symbols and arrows and things happening in it. But every time you see those equations, just remember that the premise is they stay still. And I'm going to show you that in this lecture. So before we can do that, let's talk about what a force is. So a force is a product of mass and acceleration. Something in kilograms times acceleration, and that is based on Newton's second law. Force has a magnitude and a direction, so that means it is a vector. A vector doesn't have to be just a force, but a force is a vector. A vector we're going to talk about in just a second. The common unit for force is kilonewtons or newtons, depending on what scale you're talking about. We're going to switch back and forth. In this term, we're going to talk a lot about things in kilonewtons. Next term, we're going to have to jump back and forth between newtons and kilonewtons, but a kilonewton is just 1,000 newtons. 1 newton is equal to 1 kilogram meter per second squared. That is a ridiculous unit to write, which is why we developed the term newtons. So we're going to start building on that now. A force has a magnitude, so F would have a value, and it has a direction. So we would be able to talk about it in terms of its position relative to our X, Y, and Z axes. Now, X, Y, and Z are a universal way to talk about our coordinate system. There are other ways to talk about it as well, but the majority of the time, this is how we tend to talk about things. A vector, we write it all kinds of different ways. We're going to, I'm showing you all of these, but this one right here is the way we're going to talk about it the most. We're going to have a value written here, and direction will be implied from context, such as an arrow or a verbal description, or we will write what it is, such as the angle written beside it. You can write it as a line on the top. A line on the top with the sidebars on it means we have a value but no direction applied with it, but we know that it should. If we have subscripts here, that might mean if we're talking about an X, Y, or Z subscript, that means it is along that principal axis. Or if we have multiple vectors or forces, we might do a subscript to talk about which one of them we're talking about. So vectors can be added, but it is not always a linear addition. To be added linearly, they have to be going in the same direction. An easy way to graphically talk about vector addition is the premise of tip to tail, which basically means we take all of our vectors and we draw them out and we keep adding them up from tip to tail, and then wherever it stops, we can draw from the tail of the first one to the tip of the last one, and that is the addition of all the vectors. So if that's vector 1, and that's vector 2, and that's vector 3, and that's vector 4, we can sum them all up with the total vector. So if we happened to be talking about forces, we had force 1, 2, 3, and 4, the summation of all of those is starting from the tail of the first one to the tip of the last one. If you were drawing these to scale, you could use your ruler and actually do this. If you were using AutoCAD, you could draw these to scale. If you knew what angle that was, you could draw these to scale and then calculate exactly what that is. The way AutoCAD does it is the exact same way I'm going to show you numerically. It actually uses a vector premise. So we often will break vectors into components because if they're linear, we can add them. If I had vector 1 and I had vector 2, so vector 1 and vector 2, if they're in the same direction and we follow that same tip to tail premise, I'm going to use the green one because I like to use red for reaction, we can see that it's a linear addition. So if they're in the same axes, it's very easy to add them up. So if we have a bunch of different vectors, Sorry, I should always just get my blanket before I start. If we have a bunch of vectors, we'll often break them up into their components because it's a little bit easier to add them up. If we break them up into their x and y components, you can see x and you can see y, because this is a tip-to-tail summation, so that's the x component and that's the y component, and they should equal the total component because the tip-to-tail premise is still working here. Well, the summation of these, look at this. This makes a right angle triangle. If you guys remember, we talked about right angle triangles in the very first lecture, and that is Pythagorean Theorem. We have our force, our x component and our y component of our force, and a right angle here. Well, that means fx squared plus fy squared equals f squared. We could rewrite this in whatever way we want. If we knew any two sides, we could break this up however we needed to. So f equals the square root of fx and fy, each of them squared. So we often will call it the square root of the sum of the squares, but if we know the x component and the y component, we can add it up to get our f component. If we knew what that angle there was, which maybe if we knew these two sides, we could figure out that angle, or if we knew that angle and that force, we know that we have our sine, cosine, tangent rules. So the sine of that angle equals fy divided by f. The cosine of that angle equals fx divided by f. And the tangent of that angle equals fy divided by fx. So if we knew this angle and that force, we could then break it out and find fx and fy. We could rearrange these equations to find whatever components we need. Can you work in 3D? Yep, 3D is the exact same thing. You can see if I just draw this force, it is a total pain in the butt to know what direction that is. Is that just in the x and y plane? Or is there some component in the z plane? Well, if I drew it out this way to show its 3D elements, we know that we could have our x component, our z component, and our y component, and our tip-to-tail premise still works. The summation principle, Pythagorean theorem, can be extrapolated to 3D. So the square root of fx squared plus fy squared plus fz squared would equal f. So what do we do if we have two components that aren't on a major axis? If we have f1 and f2, we know we could draw our tip to tail. We could start here and draw to here, and we'd get our total component. But it's hard to kind of do that mathematically, but we know that we can break f1 into x and y, and we can break f2 into x and y components. So f1 we can break into f1x and f1y. f2 we can break into f2x and f2y. We can sum up f1x and f2x are in the same plane. That's a linear addition. We can add up f1x and f2x, and we get an x component. We can add up f2y, or f1y and f2y, and get an fy component. And now we have the big green triangle, which is still a right angle triangle, and we have fx and fy. We can now figure out f. So if you break f1 into x and y components, f2 into x and y components, sum up all your x's, sum up all your y's, you can then figure out what your total f is. So here's the process worked out here, actually written out mathematically. We are going to do examples like this. So let's actually take this example where we have f1, f2, and f3 and figure out what the total force is. We want to know the total resulting force or the resultant force. This is not a reaction. We're going to talk about reactions later. But this is the sum of these forces. We want to know what this total force is. Remember, this shouldn't say force. This should say vector, because we are not dealing in forces. Take a look at that. It is actually in meters, not in kilonewtons. So saying it's a force is a little bit silly, but it is a vector. A vector doesn't have to be a force. So as long as we have a magnitude and a direction, we have a vector. These vectors happen to be distances. If we were walking 7.5 meters in that direction, 5 meters in that direction, and 10 meters in that direction, we want to know what the total is. Or if we wanted to know the straight line distance of all of those, we want to know what the total is. Let's look at it tip to tail, because I always get this question. It's always helpful. No matter what I do, you should always take a moment and off to the side, maybe with a piece of tracing paper, draw something tip to tail. And then you will have a rough idea of what your final calculated answer is going to be. I always find it helpful to, before I do any math at all, stop and think what the answer might be. I always say everything you need to know about engineering, and this, everything you need to know about vectors, you actually already know. I'm just showing you how to do it mathematically. So let's take those three vectors. So this was the three vectors. I've drawn them all tip to tail. That should be our resulting vector. Now, people always say, well, what if I don't draw those vectors in that order? What if I don't draw 1, 2, and 3 in the same order? Doesn't matter worth a lick. It's the same. Let's draw them in a different order. Same three vectors, drawn in a different way, same resulting vector. Let's draw the vectors in a different order again. Same resulting vector. Let's now do it mathematically. So we're going to take those three vectors and we're going to do it mathematically. Okay, we're going to solve this example where they've asked us to find the total vector. So determine the resulting vector of vector f1, vector f2, and vector f3. If we look, we see that all of our vectors are in m's or meters, we're assuming, and we have all of our angles written out right here. We want to find the sum of these. We looked at drawing it tip to tail 3 different ways, but now we want to do that mathematically. We've graphically drawn something that we think looks right, and now we're going to actually prove that mathematically. I am right up here, for my own kind of mental well-being, going to write out Sokotoa. Oh my gosh, I'm not even doing that right. I need more coffee, I think.
I got one on for you.
Oh, you're the best. So I'm writing Sokotoa out here just so that I have as this quick handy reference that I can look at when I'm doing my angles. All right, let's start one vector at a time. It's probably easiest to break it up into its x and y components, add those up, and then find the total value. So let's take a look at, let's start with vector f1. We're going to break vector f1 up into its x and y components. And here I'm going to make this bigger for you so that you can see it just a little bit easier. I'm also going to take a drink of coffee. Okay, that's going to help. So let's break f1 up into its x and y components. I'm going to redraw f1, and we know that it is 10 meters. And we want to break it up into its x and y components. So we're going to have f1x, and we're going to have f1y, and those are what we need to find. Well, look at this. This is a right-angled triangle, which means we can use SOHCAHTOA if only we knew the angle, which they did in fact give us as 22.5 degrees. That means we have the ability with this dimension and this angle to calculate the value of f1x and f1y. Let's take a look at our f1y. It is opposite our angle that we know, and that is our hypotenuse. So opposite and hypotenuse is sine. So sine of our angle should equal, or does equal, opposite divided by hypotenuse. Or for us, f1y divided by f1. What we want to know is f1y. We can rearrange this, and f1y equals f1 times the sine of our angle. We know our f1 and we know our angle. That's 10 times the sine of 22.5 degrees. We can calculate f1y, and we get that f1y is 3.83 meters. Let's just plug that in so that we can see that. I've got my calculator in degrees. 10 times the sine of 22.5, 3.83 meters. I find it handy to just keep track of what direction things are going. Arrows, you're never going to go wrong by drawing yourself a little arrow to remember what's going what direction. What are you eating?
Carrot bread. Oh, these?
Nah. All right, let's break F2 up into its component elements now. So F2 went like that, and it was 22.5 degrees from the y-axis. We want to break this up into its F2x component and its F2y component. Doesn't matter if I draw it here and here or here and here, because it's going to give us the exact same resulting vector. So that doesn't really matter. I'm wondering if this will be better if I turn that off. Yeah, that might be a little bit better. So let's do it using this angle right here. Oh, we didn't finish f1x. I am absolutely out of it. Okay, let's come back up here. We didn't break this one up into its x component. We just got our y component. So we have our angle is here, so our f1x is our adjacent side, and we have our hypotenuse. Adjacent and hypotenuse is cosine. So the cosine of our angle is f1x divided by f1. We want to know what f1x is, so we can rearrange this. f1 times the cos of our angle equals 10 times the cos of 22.5 degrees. f1x we calculate to be 9.24 meters. And look, you can see from our arrow, it's going in that direction. These numbers seem to make sense relative to each other. It looks like if we broke this up, that this should be much bigger than that. And somewhere around that range, that seems scale-wise to be a pretty good kind of comparative number to each other. All right, let's come back down to F2. We have our angle here, and F2y is the adjacent side to the angle. Adjacent is our cos. So cos of our angle is going to be F2y divided by F2.
We want to know what F2y is. So if we rearrange that, it's F2 times the cos of our angle. We know that F2 is 5 meters. So 5 times the cos of 22.5 degrees. We can calculate that. 5 times the cos of 22.5. That gives us 4.62 meters going in that direction. Our F2x is the opposite side of our angle. So opposite and hypotenuse is sine. So the sine of our angle is F2x divided by F2. We're interested in F2x, so we rearrange this equation to be F2 sine our angle. And we know that F2 is 5, and we know that our angle is 22.5 degrees. So we can calculate that out. 5 times the sine of 22.5 equals 1.91 meters. Let's look at our little diagram. Our F2x is going in that direction. It seems to make sense that our F2x is smaller than our F2y looking at this diagram. So those numbers, there's no red flags that I did something wrong there. Doing that little visual check can often be quite handy to help make sure you haven't made a mistake. Now, this is where I'm going to give you a tip on the way I always do things. I hate having to write this out, and I hate having to think about it. I would prefer if my y was always using sine and my x was always using cosine. But look, my angle is here. What if I wrote this in a different way? The exact same thing. This is still 5 meters. They gave us this as 22.5 degrees. F2x F2y. This angle here, I'm going to call it the prime version of it. The prime, this is 90 degrees. So 90 minus 22.5, we're going to end up with 76.5 degrees. So now I can always do my sine to figure out my Fy and my cos to figure out my Fx if I always reference my angle from my x-axis. You don't have to do it that way, but I find it really easy to kind of keep track of things that way. I can tell at a glance if it's got a sine in it, I'm talking about my Fy's. It's one less thing that you can do wrong. I find that very handy. But let's just double check. Let's see if we get the same information. Graphically, it looks like it should be the same, but let's just check. So now our F2y is the opposite side, or the sine. Sine of the prime of our angle is F2y divided by F2. We want to know what F2y is. We rearrange this. We've got F2 times the sine of our angle, or 5 times the sine of 67.5 degrees. Let's plug this into our calculator. We've got 5 times the sine of 67.5. We get 4.62 meters pointed upwards. So we get the same number. Let's just be very thorough here. The cos of our angle gives us our adjacent side. or f2x. We can rearrange this. f2x is going to be f2 times the cos of our angle, or 5 times the cos of 67.5 degrees. And we plug this in, 5 times the cos of 67.5, we get 1.91 meters. I always like to draw my little arrow so I don't lose track of things. And look, I get the exact same information that I did here. So let's just put a bubble around this because it's an alternate way to do it. But I'm probably now, no matter what angle I'm given, going to consistently reference it from the x-axis. Not that there's anything wrong with doing it this way, but I just find it very thorough or very comprehensive to always do it off of the x-axis. I'm less likely to screw up. So let's break F3 up into its x and y components now. So F3 was interesting because it went in a different direction. It has a value of 7.5. meters, and it is 45 degrees from the x-axis. Let's break it into its x and y components. F3x and F3y. So we can break it up into its x and y components. We have it referenced to the x-axis, so we know that sine should be associated with our y dimension and cosine should be associated with our x dimension. But let's just take a look. Our F3y is opposite our angle, so opposite hypotenuse, SOHCAHTOA, sine. So we have sine of our, what angle did I draw here? Angle equals F3y divided by F3. We can rearrange that. That F3 times the sine of our angle, well, we know what F3 is 7.5, and we know our angle is 45 degrees. So we can calculate that out. 7.5 times the sine of 45, we get 5.30 meters. Let's do the same thing for our for our x component. It is the adjacent side, so it's cos of the angle is F3x divided by F3. We can rearrange that, and we have F3 times the cos of our angle, or 7.5 times the cos of 45 degrees. We plug that into our calculator. We have 7.5 times the cos of 45. Oh, look at that. 5.3 meters. Well, it looks like those should be pretty darn close to the same. And in fact, if you know anything about equilateral triangles, you know that that should in fact be equal to each other. So now we have 3 y components and we have 3 x components. If we draw these tip to tail, we can sum these up. We know that we can do it mathematically. Oh, let's draw ourselves some arrows here. This one's going in this direction, and that one's going in that direction. So let's take a look at our x component, or let's do it in the same order we've been doing it. So let's let's sum up all the forces in the y direction. So that's everything going up and down. Well, way up here, we had 3.83 going upwards. Here we had 4.62 meters going upwards. And here we had 5.3 going upwards. We can sum those up. We get 3.83 plus 4.62 plus 5.3 equals 13.75 meters going upwards. Let's sum the forces in our x direction. So way up here are from our F1x, we have 9.24 going in that direction. F2x, we had 1.91 going in that direction. And then here for F3x, we have 5.3 going in this direction. So these are trying to cancel each other out. So we're going to say that that's going in the negative direction. It's going opposite the other two forces. So we have 9.24 plus 1.91 minus 5.3. We get 5.85 meters. So now we have a brand new vector. We have a brand new vector, and let's draw our arrows for these. This was a positive number, so this was the sum of all of these was still going in that direction. All three of these were all going upwards. Let's draw ourselves that little diagram. Let's draw these new vectors. So we had 5.85 meters and 13.75 meters. I haven't drawn the scale that great, but we're getting a pretty good idea of it. We can draw our tip to tail resultant. We can get our total force F, and that's what we want, and we wanted to know the resultant vector, so we need a force and we need a magnitude and a direction. So we need to know what the value of that is and where it is in the world. Well, this is still another right angle triangle. We've got another right angle triangle here. If we've got a right angle triangle, force is going to be the square root of the square of each of our sides. So the square root of 13.75 squared plus 5.85 squared. And we can plug that into our calculator. We've got the square root of 13.75 squared plus 5.85 squared. And we get 14.94 meters. And we want to know where it occurs as well. We want to know what that angle is. We've got opposite and adjacent, so that's tangent. Tangent of the angle equals opposite, which is our fx, divided by our our opposite is our fy, divided by our fx, which is our adjacent. We want to know what the angle is, so we can rearrange that. The angle is the inverse of the tangent of fy divided by fx, or tangent of fy is 13.75 divided by our fx, which is 5.85, and we can plug that into our calculator, and we get, I have to use my second function here, the inverse of my tangent, 13.75 divided by 5.85, and we get 66.95 degrees. So we have calculated the total meters and its location. So we have summed up those three vectors that were given to us. So we have found the resulting vector, or the sum of all of those vectors. Let's just bring this down a little bit. So these were our three vectors. And you can see that written out here. So we've got the sum of all of our vectors is 14.94, and our angle is pretty darn close to 97 degrees, or 67 degrees. And here it is worked out again for you.
So if we have all of those forces that are vectors acting on our object, we want to make sure it's not actually moving. Remember, statics means it is not moving. We want it to be in equilibrium. We want it not to be sliding around. So if we have multiple forces acting on our object, but we want to know what it takes to be in equilibrium, we can figure out what reaction must be there to stop it from moving. So each structure is subjected to a series of loads that try and move the subject or the structure. There's weight, there's live load, there's wind, there's earthquake. We want the structure not to move or remain in equilibrium or be static. To remain in equilibrium, if we summed up all of those forces and found our resulting force, there must be some reaction, some equal and opposite force that's keeping it in place. That's our reaction. We want to know what reaction must stop these things from moving in space. So if we have a force acting on an object, we want the sum of all of those forces to be zero. We want it not to be moving. So force 1 plus some unknown reaction, well, there must be an equal and opposite force. See, look at that. We've got a negative there. These two are equal, but the reaction is in the opposite direction. So graphically, you know that this is what it must be. Here it is mathematically. This just means that the sum of all of the forces must be zero. We want F1, we have F1 acting on it, and we want to know what reaction must be stopping this thing from moving. So F1 plus some reaction must equal zero. F1 has to equal the reaction, but be in the opposite direction. So this is graphically this information right here. Well, what if we had two forces acting on it? We can go about this two different ways. We can sum these forces and then find the equal and opposite reaction. So F1 plus F2, the sum of F1 plus F2 plus some reaction means this thing isn't moving, or the sum of all of the forces must be zero. So our reaction must be an equal and opposite vector from F1 plus F2. Now there is another way we could do it, and I wish I had written it out here for you, but we could sum the forces here, and we could sum the forces here, and we could, actually, you know what? I'm going to stop this and I'm going to make that slide. I'm going to come right back to that with you guys. Okay, so I added the slide I wanted to show, which is just demonstrating that you can either sum up all your forces by figuring out what the resultant is, and then determining your reaction. But it might be easier to find the reaction in each major direction and then sum up to find the total reaction. So we had looked at it. Did I then put the slide in the wrong spot? Yeah, so we had looked at it like this. We had looked at it
like this, where we had two forces and we summed them up, and then we figured out what it took for it to be in equilibrium, or for the sum of all of the forces to be 0, and we were able to find the equal and opposite reaction. So if we had those same two forces, we could do the exact same thing in a slightly different order, but it is the exact same thing. We can find the reactions in X. So what does it take for X to be in equilibrium? Everything must sum up in the X direction to be 0. So Rx plus F2x must equal 0, and F1 plus R1 in the Y direction must equal 0. So Ry must be equal and opposite to F1, and Rx must be equal and opposite to F2. Then we can take that Ry and Rx and find the total reaction. Both are legitimate ways to do it. And we're going to see that the second way of doing it is probably going to make our life a little bit easier as we go forward. But we can do it either way, and we're going to do an example where we do it both ways just to show you that it works out the exact same. So let's take a look at this unknown object, and it has 3 forces acting on it, 3 vectors. We're assuming forces because it says F, but it could be something else. Unless they gave us a value and told it was a kilonewton, then we'd know for sure it was a force. But 3 vectors acting on this point, we have F1, F2, and F3. We can do the tip-to-tail summation here and find the total resultant, or the sum of all of those vectors. And then the equal and opposite vector must be what's happening there to keep it in equilibrium. So let's do where's the question? Did we already do it? Oh, yeah, sorry. Because I film all of the recording and then go back and do the examples separately, I was very confused about where the example went. Okay, so previously, for you, I haven't actually recorded it yet, but you're going to see it in order. We figured out the sum of all of the forces. So we had all of those different forces, which are vectors, and we figured out their total, and we figured out its angle, so its magnitude and its direction. We want to know what it would take to keep all of those forces from moving this object, or the equal and opposite reaction for them. So this happens to be meters. So if we had things going in this direction and we wanted to stop it, we would have an equal and opposite reaction. Let's now do an example where we find what it takes for this system to be in equilibrium. So we have some unknown system that we've represented as a dot here, and we have 2 forces on it. F1 of 2 kilonewtons, 70 degrees from the x-axis, and we have 5 kilonewtons, 120 degrees from this x-axis. I often like to keep all of my things referenced from the same axes, and in fact, that is an obtuse angle. I would like an acute angle, so one less than 90 degrees. I'll probably go and figure out what it takes from that side. But I want to know what the reaction is to stop this from moving or to keep it in equilibrium. I will show you both ways of doing it, and we'll do that now. Okay, we've been asked to find what reaction will keep this system in equilibrium. We've got some force going in this direction, some force going in this direction, and they have some direction associated with them based on the angle. And we want to know what reaction stops this thing from moving. What will make sure that this isn't moving up and down or back and forth. So if we start, there's 2 ways we can do it. We can break each of these up into their x and y components, find the resultant, and then say that the reaction has to be the equal and opposite force. And that is definitely a valid way to do it. Alternatively, we can break it up into its x and y components, find out what it takes for the x and y directions not to move, and then find the reaction. Now, people might be skeptical of how those two things both equal each other, so I'm going to do it both ways. But then after this, we're probably going to only do it the second way. We're going to consistently break things into the x and y components, sum them up, and then find our reaction. Break things up into our x and y components, add up our x and y components, but keep them separate, and then find the reactions in x and y components. So let's go through this both ways. So we've been given an object that has F1 of 2 kilonewtons acting on it, and it is (70°) from the x-axis. Let's maybe just draw these axes in just to give us a little bit of context. And we have another force here, F2, and F2 equals 5 kilonewtons, and they've given it to us from the x-axis, but kind of from a weird way from the x-axis. It's a very wide open angle, and they've said that that angle is 120 degrees. So let's do what we did in our last example, where we break it up into our two components. So we've got, let's look at F1 first, and we're going to break F1 into its x and y components. So I just want to see how I did my color scheme for that. Okay, that'll work. So let's draw our F1 all by itself, and F1 is 2 kilonewtons. And we know that the angle is 70 degrees, and we want to know our F1y and our F1x components. We know, based on SOHCAHTOA, and if we're always referencing from the x-axis, that our F1y equals F1 times the sine of our angle, or 2 times sine of 70 degrees. We can plug that into our calculator. 2 times the sine of 70 degrees gives us 1.79 or 1.88. 1.88 kilonewtons, and that's pointing downwards. Now, it's probably going to make life easier if we start talking about a consistent positive and negative direction. We're going to say everything upwards in the world is positive, and everything to the right is positive. So if upwards is positive and to the right is positive, that means this 1.88 going downwards is minus 1.88 kilonewtons. I'm just going to write it there for myself. Both of these are correct ways to express this. One is not more right than the other. Sometimes this is going to be more handy, and sometimes this is going to be more handy. You can imagine when we're summing things up, keeping it in positive and negative values might make life a little bit easier. F1x is F1 times the cos of our angle, or 2 times the cos of 70 degrees. We can plug that into our calculator. 2 times the cos of 70 is 0.684. We're going to keep 2 decimal places. 0.68 kilonewtons. And look, it's going in that direction. That's the left. We said that everything going in the right direction is positive. So another way we could write this is minus 0.68 kilonewtons. Both of those are correct ways to write that information. Let's look at F2 now. F2 has a value of 5 kilonewtons, and we want to break it up into its F2y component and its F2x component. They told us that that angle was 120 degrees. Because we want to work with our right angle triangle, that is going to be an easier number for us to work with. So let's figure out what that angle is. This, something completely wide open, is 180. And to get to there was 120. We're left with a 60-degree angle. So if we want to find our F2y value, it's the opposite of our angle. So we have F2y equals F2 times the sine of our angle, or 5 times, the sine of 60 degrees equals, so 5 times the sine of 60 degrees equals 4.33. Let's just take a look at what direction that's going. It's going downward, so it might be easier to just talk about that as a negative 4.33 kilonewtons. Both of these are right ways to express that. We have a value and we have a direction, because we've said that this is the y direction. Let's do the same thing in our x direction. We've got F2 times the cos of our angle, or 5 times the cos of 60 degrees. We can plug that into our calculator. 5 times the cos of 60 is 2.5. And that is going in that direction, or positive 2.5 kilonewtons. Because remember, anything going to the right of the page is positive. Now this is where we can do one of two things. We can sum these up and then find the resultant, or we can sum up the x and y directions and find their independent reactions, and then find the total reaction. So let's start by doing it by finding the total resultant. So let's do it by finding this total force. So we're going to do it by finding the total force. So the first thing we need to do is figure out what our x and y forces are. So let's sum our forces in the x direction. Let's just write a note for ourselves that we're saying anything that goes to the right is a positive number. So we can come back up here. This is going to the left, so it's a minus 0.68. And then down here, anything going in that direction is positive, so plus 2.5. We sum these up, and we get 1.82 kilonewtons going in that direction. So that was a positive. We can sum the forces in the y direction. So we want to take all of the components that we broke up into y's and add those up. We're reminding ourselves right here that anything upwards is positive, which means anything downwards is negative. We have 1.88 kilonewtons downwards, which we know means it's a negative, so minus 1.88 kilonewtons. And our F2y is 4.33 kilonewtons downwards, or minus 4.33 kilonewtons. We sum these up and we get minus 6.21 kilonewtons. Or we could rewrite that as 6.21 kilonewtons downward. Again, both of these are correct ways to write this information. Now we have an x component and a y component. We can draw this. We have an x component or a y component that comes down, 6.21 kilonewtons, and we have an x component going to the right of 1.82 kilonewtons. We know that there must be some resulting force that is the sum of these. So we can draw that tip to tail. We want to know what the sum of our forces is here. Or let's maybe just call it F. So let's maybe just call this F. And we want to know what F equals. Well, look, this is a right angle triangle. That means that we have some information we can work with. We know that the hypotenuse equals the square root of our opposite and adjacents added up and squared. So 6.21 squared plus 1.82 squared. We can plug that into our calculator. The square root of 6.21 squared plus 1.82 squared. And we get 6.47 kilonewtons. We want to know where that is relative to the x-axis. So we want to figure out what angle that is. Well, we know we still have a right angle triangle, and that's the opposite side, and that's the adjacent side. So SOHCAHTOA, we have an opposite and adjacent, which is tangent. So we know that the angle is the inverse of the tangent of Fy divided by Fx, or tangent negative 1 of 6.21 divided by 1.82. And we plug that in. Let's calculate that. Second function, tangent, 6.21 divided by 1.82. And we get 73.67 degrees. So we know that we have a force F that is 6.47 kilonewtons, 73.6 degrees from the x-axis. We know that for there to be a reaction that stops whatever this point is from moving, there must be an equal and opposite reaction. So a reaction must be the same value, but going in the opposite direction. And so we can see that from our diagram. There's an arrow associated with it. So we can see that we have an equal and opposite reaction. Now, this is a completely valid way to do it, but sometimes we just want to jump right to finding our reaction. We don't care what the sum of the forces is. What we care about is what's going to keep these two forces from moving our object. So let's do the same thing, but we're going to directly find our reactions. So instead of total force first, we're going to do X and Y reactions. So by doing this, when we do our sum of the forces in the X and the sum of the forces in our Y, there must be something that stops this from moving. We can even draw this out if we wanted. So let's take a look at our X direction first. We had our F1x moving this way, some amount, and our F2x moving that way, some amount, and then we must have some reaction that stops this thing from moving. We don't know what direction it goes in, but we know it must be there somewhere. So let's sum up our forces here. Let's try this by doing it mathematically. And in fact, we don't know what direction this reaction is. I'm going to guess that it's going in the positive direction. Just because I don't know. I mean, graphically, we can look at this and we can guess that it's probably going in that direction. But we don't know. That's a pretty big assumption. Let's try it mathematically and see what we get. So let's sum up our forces in the X direction. And we're saying we want to know what it takes for this thing not to move. The sum of all of these forces has to equal 0 for this not to slide back and forth. So we have our F1x plus our F2x plus our reaction. All of those have to equal 0. Well, let's take a look at what those values were. Our F1x was going in this direction, so it's a negative. So minus 0.68. And then our F2x is going in that direction, which is our positive direction, so plus 2.5. Our reaction, we don't know what it is. We're going to assume it's going in the positive direction for now, but we might be wrong. Let's draw it going in the positive direction. When we calculate this and rearrange it, we rearrange this equation and we find that let's actually call it Rx, that Rx equals minus 1.82 kilonewtons. So that's telling us that the arrow we drew is wrong. So our Rx is actually going in the negative direction. Let's sum our forces in the Y direction. Everything going upwards is positive, and we want to know what it takes for this thing not to move. For it not to move, all of the forces must add up to 0. We know there is some unknown reaction that is making that happen, and we want to calculate what that is. So we have, if we come back and look at our calculations that we did earlier, we have our F1y that is moving downwards, or minus 1.88. We have our F2y, which is also moving downwards, which is minus, and some unknown reaction. We rearrange this and we find that Ry equals 6.21 kilonewtons. We assumed that Ry was going upwards by saying it was positive, and it looks like that is in fact the case. So we have an Ry that is positive. So these are our X and Y reactions now. Let's draw those two things. Let's draw that out. We have maybe I'll draw it in black first. We have 6.21 going upwards, which is our y, and we have our Rx, which is going in the negative direction. Our Rx equals 1.82 kilonewtons. Draw our tip to tail. There's our total reaction. And we want to know what this is relative to the x-axis. So we have some unknown angle here that we want to determine. Well, look at this. We have a right angle, we have a opposite side and an adjacent side. So we know that R equals the square root of 6.21 squared plus 1.82 squared. And we've already done this calculation before, and we get that the value is 6.47 kilonewtons. And our angle here is relative to the x-axis, with y being our opposite side. So our angle equals the tangent -1 of our 6.21 divided by 1.82, and we get 73.67 degrees. So it doesn't matter how we do it, we get the same answer. We get the same value of 6.47, and we get the same angle relative to the x-axis, but we skip this step of finding the sum of the forces. We just went straight to finding the sum of the x and y components, including the reactions. Let's minimize this and take a look at those slides. So here it is worked out. And here you can see it drawn that it didn't matter which way we did it. These two forces summed up and stopped from moving required this reaction at this angle. So this is what it took for this element not to move in space.
Okay, let's talk a little bit about how the different loads actually cause reactions, or what they're doing to the object. Mostly just so we can talk about what the reactions are. I said that force is mass times acceleration. So is a body at rest experiencing no forces since it's not accelerating? No, it is actually accelerating. You right now are accelerating to the center of the earth. But you have the ground contributing an equal and opposite reaction to your force. So your mass times acceleration of Earth is pulling you down into the center of the Earth, but the Earth is pushing back up with an equal and opposite reaction. If you guys remember physics, and I remember doing this in grade 10 physics, the Earth is actually moving towards you based on the acceleration you cause on the Earth. But it's such a small amount. But the forces, equal and opposite reactions. So mass of Earth is accelerating towards you, but with a very small acceleration, equals the same equal and opposite reaction, or I guess equal and opposite reaction. So therefore, a motionless body must be held in place by a force equal to the mass times acceleration due to gravity. This is what we call weight. And weight can differ if you're on a different planet. Your mass remains the same, and if you I can't even remember what year it was, but some dude got in a bath and displaced water, that is mass. And that remains the same no matter where you are. You would displace the same volume of water no matter what. Your weight does change based on the acceleration of the planet you're on. We're on Earth, and acceleration is 9.806 blah blah blah, but 9.81-ish is good enough. So let's take a look at just a fun example. This isn't a hard example, it's more just to be silly. So I am standing on Earth. My mass is 140 pounds. If I convert that into kilograms, so you can go online and find the conversion for pounds to kilograms, that is 63.5 kilograms. I want to know how many kilonewtons that is. Well, it's my mass times acceleration, and acceleration on Earth is 9.806. I'll often write 9.81, pretty darn close, meters per second. So here we have our kilograms, meters times meters per second squared. We know that is a Newton. So 63.5 kilograms times 9.81 meters per second squared gives us 623 newtons. So my weight is 0.623 kilonewtons. Now, in imperial, pounds and pound force are the same thing. They work out to be the same thing. They've set up their system to be the same thing. So sometimes I'll take this number and make the conversion happen directly. A lot of engineers will do that because they'll convert from pounds right into kilonewtons. But you now know how to figure out the kilonewtons of the weight of any object. You're going to do one for fun in your assignment where you have people in 3 or 4 different weight types. So pay attention to the units. If you don't know the conversion, the internet is a wonderful thing. I think I even throw a weight of one person in stones in there. So you'll have to look up what all those conversions are and convert them all to kilograms, and then figure out how many kilonewtons the people are. What if I've worked really hard and I go to the moon? The gravity on the moon, or the acceleration, or the amount we try to rush down into the center of the Earth, is 1.6 meters per second squared. My mass stays the same. I'm still 140 pounds. 140 pounds times, not the right number here. So 140 pounds, change that to kilograms, I get 63.5 kilograms, still a mass. And then I take my mass times the gravity of the moon, or the acceleration that the moon would exhibit on me, is 1.6 meters per second squared, and I get 103 newtons, or 0.103 kilonewtons. We have, the internet is crazy, and a bunch of JK kids just can't log on every day, and they get marked as truant, and it is heartbreaking when they're supposed to be carving pumpkins and they cannot log on to their class to carve their pumpkins. So sorry about that. So depending on what celestial body you're on, your weight will be different. Now, let's face it, most of us are going to be here on Earth for our entire life, and so our weight is going to be the conversion of kilograms times 9.81 meters per second squared to give us kilonewtons as our weight. So that was just a fun one. How does wind react with an object? So wind is air in motion. It's a fluid medium. It has a mass. It's a very, very, very tiny mass, but it has a mass. Wind causes force when it interacts with a body or structure because the body must produce an acceleration on the air particles for them to move around the object. Basically, for wind forces, the body doesn't accelerate. The body makes the wind mass accelerate. So we are forcing the wind to move around us, which is causing the wind to accelerate. Earthquake. The body is accelerating. It's actually moving. But it's slightly different. The Earth moves like this, and it makes the body move with it. the Earth is exerting a force on a body, causing it to move. So instead of just sinking down into the center of the Earth, it's trying to throw the object somewhat. But that's really hard to kind of imagine that the object is moving. What we do instead is we say that our object stays still, and this lets us consider the body anchored to Earth as a static element, and we frame our reference accelerations due to the earthquake similar to gravity. So we say that we relate the amount that it's trying to move sideways as a percentage of the amount we're trying to go down into the world. That relationship is acceleration produced by the earthquake. So mass times the acceleration of the earthquake. And different earthquakes have different accelerations, but they've done enough statistical analysis to determine what that acceleration would be in each zone. We know what the acceleration of Earth is, or what it tries to pull things, or it causes objects to accelerate with. And if we know accelerations of earthquakes that we've determined statistically, we can relate those as a ratio to each other. So that's where the earthquake can be talked about as a percentage of weight, because we know that our weight was determined by mass times the acceleration down into Earth, and we know that the acceleration of the earthquake is a ratio of that. So we just jump right to the end and take earthquake forces as a ratio of our gravity forces. Pressure and reaction. We're not going to do much with this. So this is pressure, so outwards force, so blowing into a balloon, for example. The fluid is not in its natural state, or whatever the air fluid is. It's not in its natural state. So for compressed air in a vessel, the particles are trying to accelerate away from each other. And when they do that, they're pushing out on the object. Water in a glass is trying to accelerate down into the Earth. And so it's trying to fall flat. So at the bottom of the cup, there's more force pushing outwards. Very similar to our hole in the ground with the dirt trying to fill out into the hole. To resist the particles accelerating out of the vessel must exert a force on the fluid or medium to maintain equilibrium. We're not going to really get into that, but it's nice to know how that's created. So let's do an example. We're going to do two examples now, one with a person and earthquake forces, and one with a billboard and wind forces.
Okay, this one's more for fun than anything. We have somebody standing in their living room when an earthquake hits. The quake produces a lateral acceleration equal to 15% of gravity. It's just after the holidays, so you're carrying a bit of extra weight, topping the scales at 85 kilograms. What is the reaction required for you to maintain equilibrium? Magnitude and direction must be included. So what reaction do you need to not move? What reaction has to happen for you not to move? So let's make this a little bit bigger, and we'll go through that calculation. Sorry. So, earthquake. We have someone with a weight that we don't know what it is, but we know weight is mass times acceleration. And acceleration on the Earth is gravity. They were 85 kilograms times 9.806 meters per second squared. We calculate that and we get 833.51 newtons, because newtons are kilograms meters per second squared. This is right, but I find it easier sometimes to write these things in kilonewtons, especially when we're talking about forces and resultants and reactions. 0.833 kilonewtons. Again, newtons or kilonewtons, both right, they're both force, but often when we're talking about forces, we start to talk about things in kilonewtons. We're going to see next term that there are times where we keep things in newtons, or we will put things into newtons, but that will become more clear next term when we talk that through. Now we have another force acting on this, and it was a lateral force. Well, actually, let's just draw ourselves a little arrow here. I'm trying to sink down into the world there. So that force is going downwards. We might even want to say that it is the same thing as negative 0.833 kilonewtons. Both of those two things are the same. Earthquake, we know, they told us, was 15% of weight, or 0.15 times weight, which was 0.833 kilonewtons. So 0.125 kilonewtons. They didn't tell us what direction this earthquake is going. Let's say it's going in that direction. We could pick it. An earthquake would throw us either way. So let's start with the earthquake going in that direction. We can draw this. We have our 0.833 kilonewtons downward and our 0.125 kilonewtons in that direction, and we want to know what our reaction needs to be to stop this. So we can do this one of two ways. We can sum up these forces and then find the reaction, or we can go right to the reaction. I'm going to do it different in this than I give you the answer in the slideshow, just so that you have both. So this is our reaction X, and this is our reaction Y. We want to figure out what those two things are. Sum of the forces in the Y, with everything upwards being positive, well, we have minus 0.833 plus our Y needs to equal 0 because we want to know what it takes to be 0. We can rearrange this and we get that our Y equals 0.833 kilonewtons upward. Sum of the forces in the X, we want to know what it takes for the sum of all of the forces in the X direction to be 0, so that this person doesn't fly off into space. Well, we have our 0.125 kilonewtons going in that direction, which is positive. And I have drawn Rx going in the negative direction. Now, I could have drawn Rx in the positive direction, and if I got a negative answer, it would say that my arrow was wrong. I'm going to rearrange this, and I get that Rx equals 0.125 kilonewtons. So I have drawn my negative reaction correctly. I didn't know what way it was going, but I drew it in the negative direction, and I was right, because my positive does not contradict my arrow. I included that negative here in my calculation, so this positive answer tells me that I'm right. So that means I can redraw this as .833 and 0.125. Let's just dash in these values here. I now want to find what this total reaction is. The reaction is going to be the square root of my two sides, or the square root of 0.833 squared plus 0.125 squared. And when I calculate that, I get 0.842 kilonewtons. And I want to know its angle relative to the x-axis, and that is tangent -1, or the inverse of the tangent, of my opposite over adjacent. My opposite is my y, and my adjacent is my x. I can calculate that that angle equals 81.47 degrees. So for this person experiencing an earthquake, I need this reaction to stop them from moving up and down or back and forth. Does it seem like anything might be missing from this? You don't have to answer that, but next week we're going to start thinking about the fact that this person might just tip over. So they might not move back and forth, and they might not move up and down, but they might just tip over, and we need to start worrying about that as well. We have one more example. We have a billboard that is 5 meters high and 10 meters wide, and it weighs 0.5 kPa and has a wind load of 1.2 kPa on it. Calculate the reaction required to maintain equilibrium for the billboard. So let's do our wind example. We have a long billboard that is 10 meters long and 5 meters high, and it has a weight and a wind acting on it. Well, we know that our W and our P, we had that our weight was 0.5 kPa and our wind was 1.2 kPa. So those are in kPa. We know what the total area is. We can figure out what the total weight is. 0.5 times 10 times 5 gives us a total weight of 25 kilonewtons. And our total wind load is 1.2 times the area, or 10 times 5, gives us 60 kilonewtons. Remember, what we're saying here is that every 1 meter by 1 meter portion of this billboard has 0.5 kilonewtons acting downwards and 1.2 kilonewtons pushing on the face of it. So if you added up all of those 1 by 1 meter sections of it, of which there is 50, you can figure out the total weight, and you can figure out the total wind load on it. So we have now a wind load P, which is in the x direction, of 60 kilonewtons, and we have a dead load downward of 25 kilonewtons. We want to know what the total load is, F, and then we want to know what it takes for this to be in equilibrium, or the equal and opposite reaction of that. Again, we can do it two different ways. Oh, sorry guys. Here I am blathering away. There was nothing profound there. We have our 0.5 kPa on the whole weight of the billboard going downwards, and our 1.2 kPa of wind blowing on the face of the billboard. We calculated both of those out, and now we've drawn our triangle of our P and our weight, or our wind load and our weight, and we know that we can calculate F, which means we can also find its equal and opposite value, or our reaction. Or we could break it up and find our Y reaction and our X reaction and then calculate R directly. Both are okay ways to do it. Let's find F. F is the square root of 60 squared plus 25 squared. And if we calculate that out, we get 65 kilonewtons. And that angle is the tangent of 25 divided by 60, or 22.6 degrees. So opposite, adjacent, tangent, the tangent of the angle equals opposite divided by adjacent, so I've just rearranged that here. And that means the equal and opposite reaction must be equal and opposite. So R equals 65 kilonewtons and is 22.6 degrees from the x-axis. Now again, this billboard, this seems great, but look, we understand that this load is actually happening somewhere up on the billboard, or we would represent that as an analogous point load happening right there in the middle of it. So we actually have a pressure pushing everywhere on this billboard. And if I had a surface element and I pushed on it, we know that it wants to tip over. So there's something missing in this calculation. We have rotation that we have to worry about. So we have an ability to stop up and down and side to side. But now we're going to need to worry about rotation. And that's what we're going to talk about next week.
So what are our takeaway tips? Statics is the study of things in equilibrium, essentially. They are not moving. Statics means equilibrium, which means it's not moving. We know that vectors are something that have a magnitude and a direction, and that's really handy because we're often talking about forces, which are a vector. We know that we can break our vectors down into x and y components, which might allow us to add them up easier. We know that based on our basic trig functions, we can figure out resultants of those. We can use triangles with right angles to use our square root of the sum of the squares, or sine, cosine, tangent laws. We know that a reaction is an equal and opposite force that's going to keep all of our things from moving. So if we have forces acting on an object, a reaction is what it takes to keep that object from moving. Or if that object isn't moving, that reaction must be there that stops it from moving. We know that if we know what those forces are, we can break it down into its x and y components. We can sum those up, and then we can figure out the reactions in the x and y components, and then we can sum those up to figure out what our total reaction must be to stop our object from moving. We also know that force equals mass times acceleration, but we're not going to do a whole lot on that. But the big thing is, if we know something isn't moving, the sum of the forces must be 0. So if it's not moving up and down, the sum of the forces in the y direction, 0. If it's not moving back and forth, the sum of the forces in the x direction must be 0. If we know there are loads in those directions being applied, we then know there must be equal and opposite reactions to keep it from moving. So those sum of x's and y forces are going to be really important, and we're going to start to use them a lot. And next week, I'm going to show you there's one more equation that we can add into our repertoire that we're going to start working with as well to really, really prove that things are in equilibrium and are not moving.